So this video is on laws of logarithms and logarithm equations. So in the last video we talked about exponentials, and these are of the form a to the power of x, where a is a number. And let's say we had a question where it was a to the power of x is equal to n, where n is a number, and we needed to find x. Well, we can do this, we can find x by using something called a logarithm. We can do log of a is the base, so it would be the base of the log like this, of n, and this is equal to x. And we can find this log base a of n using our calculator, and therefore this will give out the value of x. So for example, as you already know, 2 to the power of 3 is equal to 8. If I wanted to write this in the log form, it would be log of, and then 2 is the a, this is the base, so it's going to come down here, so it's going to be log base 2, then the 8 is the n part here, so this is going to go in the log like this. And we can use our calculator in order to get this value out, log base 2 of 8. On your calculator, under the integration symbol, we have a log button. If you press that, it gets out a blank log with 2 empty boxes. And you can put the base as 2 and the number in the bracket as 8 as shown. And if you press equals, this gives out the expected answer of 3, which is what we're expecting because we know that this is 3. We know that 2 to the power of 3 is equal to 8. Let's do another example. Let's say that 3 to the power of x is equal to 81, and we wanted to find the value of x. Well, we'll do this because it would be log, and then it's going to be base 3 of 81, and this is going to be equal to x, and if you put this into your calculator, this gives out a value of 4. And this makes sense because we know that 3 to the power of 4 is equal to 81. Let's do another example. Let's say that 7 to the power of x is equal to 51, and we wanted to find x. We would do this because it would be the log of base 7 of 51, and this would be equal to x, and if you put this into your calculator, this gives out a value of 2.02 to 2 decimal places. Now, just a couple of shorthand notations that you need to be aware of with logs. Firstly, if we have 10 to the power of x is equal to 100, and we need to find the value of x, so it would be log of base 10 of 100. Now, log base 10 is by far the most common log, to the point where we actually don't write the 10. We just write this as log of 100. Whenever you don't write the base, it is actually base 10, but we just don't write it. You can get this log base 10 quickly on your calculator by first pressing shift and then pressing this button with the kind of minus symbol that has brackets around it. Of course, you could just do the normal log button and write log base 10, etc. But trust me, it's a lot quicker to do it this way. And therefore, this is going to be equal to x, and log 100 is just equal to 2. And then one final thing you need to be aware of. Let's say that e to the power of x is equal to 7, and we need to find the value of x. So we would do log of base e, but because we talked about the prominence of e to the power of x in the last video, we have a short-term way of writing log base e. We write this as this kind of ln here, and then it will be ln of 7. Now, the way you actually say this is the natural log with kind of the n and the l the wrong way round, and that's the way I'm going to refer to it. A lot of people just say it as ln, which is what it sounds like, which is fine as well. A lot of people say it like that. You can also get this on your calculator quickly by pressing this button right diagonally to the integration symbol to get up a natural log. And therefore what we can do is we can solve from here. So it's the natural log of 7, and this is going to be equal to x. And a lot of the time with the natural log of something, they'll probably just ask you to leave it in this form rather than put it into decimals. But if they did ask you to put it into decimals, this is equal to 1.95 to 2 decimal places. We can of course do the opposite and convert a log to an exponential. So for example, let's say that we had log of base 4 of 64 and this is equal to 3. If we wanted to write this in the exponential form, it would be, so 4 is the base, so it would be 4 and then it would be to the power of 3 and this is equal to 64. Another example, let's say that we actually had a question and it said that log x is equal to 2 and we need to find x, so we need to rearrange this. Remember, this is actually base 10, but we don't really write it, we'll just leave it as log x. So this would be, remember that this is base 10, so we've wanted to write this in its exponential form. It would be 10 as the base and then 2 as the power, and this is equal to x, so therefore x is 10 to the power of 2, so that's 100. So here's some basic example of some logarithm questions. So for the first one, it's 2 to the power of x is equal to 17 and we want to find x. So to do this, it will be log of base 2 of 17 and this is equal to x, and if you put this into your calculator, this is equal to 4.08 to do this to 2 decimal places. For the second one, it's e to the power of 3x is equal to 2, so this is going to be log of base e, but remember we write that as the natural log of 2, and this is equal to 3x, so therefore x is going to be equal to, if we divide everything by 3, to get the natural log of 2 divided by 3, and this is equal to x. Now, as I said before, a lot of the time they'll probably ask you to leave it in the natural log form. If they ask you to put it into decimals, this is equal to 0.231. For the third example, it's 10 to the power of 3 minus x is equal to 100, so this is going to be log of base 10, but again we don't really write the base 10, we just do log of 100, and this is equal to the power 3 minus x. First of all, log of 100 is just equal to 2, and this is equal to 3 minus x. Minus 3 from both sides to get minus 1 is equal to minus x, so therefore x is equal to just 1. And then for the final example, this is the thing we talked about where it's the opposite, where we want to convert from a log to an exponential. So remember that the natural log is actually base e, so it's going to be base e of the power 3 over 2 is equal to 2x plus 7. Minus 7 from both sides to get e to the power of 3 over 2 minus 7 is equal to 2x, so therefore x is equal to e to the power of 3 over 2 minus 7 over 2. And again, they'll probably usually like you to leave it in the e to the power of something form, but if they want it as a decimal, it is equal to minus 1.259. This will be something talked about more in chapter 2 of year 2, but log base a of x is the inverse of a to the power of x, so therefore the natural log of x is the inverse of e to the power of x. Now the spec specifically talks about you knowing what the graph of the natural log of x is, and this is because, as we talked about in the last video, how prominent e to the power of x is in modelling and things like that. So naturally its inverse natural log of x is 2. So in order to sketch the natural log of x, any inverse is always the same graph, but it's just reflected in the line y is equal to x. So therefore the inverse of y is equal to e to the power of x is going to be a reflection in the line y is equal to x. So it's going to look something like this here. And this is y is equal to the natural log of x. So what we've seen so far is the absolute basics of logarithms, but in fact they actually have loads of properties that are really useful to exploit in loads of questions. So to do this, you really need to understand the laws of logarithms and how they work. So the first law is that the log of base a of b plus the log of base a of c is equal to the log of base a of b times c. So for example, for all the examples, by the way, I'm either going to use log base 10 or the natural log, as they're the most common logarithms that come up, but it could be any base. For example, log of 2 plus the log of 3 is equal to the log of 2 times 3, which is equal to the log of 6. Again, I have to stress the only reason this works is because the bases are the same. They're both the same thing. Here, they're both 10. We just don't really write it. Again, if we didn't, if the bases weren't the same, it wouldn't work. So, for example, if we had something like log of 3 of 2 plus log of base 4 of 2, we couldn't add these together because it doesn't work because the bases are different. The bases have to be the same in order for the laws to apply. The second law is that the log of base A of B minus the log of base A of C is equal to the log of base A of B divided by C. So for example, if we had the natural log of 6 minus the natural log of 2, this would be equal to the natural log of 6 divided by 2, which would be equal to the natural log of 3. Again, I have to stress it only works because the bases are the same here. The bases are both A. For natural logs, the base are both A. The third law is that the log of base A of B to the power of C is equal to C log of A, or base A of B, where C becomes the coefficient of the log. So for example, if we had the log of 4 to the power of 2, this would be 2 log 4, where the 2 comes down and becomes the coefficient of the log. Now, the one thing I do have to stress is that this only works when the power of 2 is in the log. If we had something like log 4 to the power of 2, this would not be equal to 2 log 4 because the square is affecting the entire log 4, but the square has to be in the bracket and individually affecting the 4 like that. And then the fourth law is that if we had A to the power of log base A of B, this would just be equal to B. This most commonly comes up with e to the power of and the natural log. So something like e to the power of natural log 2, this would just be equal to 2. Now, just in special cases to watch out for, if you have a log and a square number, such as in log 16, this can be of course written as the log of 4 squared, which can then be written as 2 log 4, with the 2 coming down as the coefficient using this law here. If we had a fraction in the log, so for example, let's say we had the natural log of 1 over 4, this is equal to the natural log of 4 to the power of minus 1, which the same thing can be applied. This minus 1 can come down as the coefficient to become minus the natural log of 4. If we have a square root in our log, so for example, let's say that we had the log of the square root of 5, this would be equal to the log of 5 to the power of a half, and this would be equal to the coefficient would come down to a half log of 5. If we had log of base A of A, this would be equal to 1. So for example, let's say that we had the log of base 2 of 2, this would be equal to 1. And if you think about this, it's quite easy to explain, because if we did this in the exponential form, so it's base 2, so it's going to be 2 to the power of, let's just call this x now, and this is equal to 2, you can see the only way that this can be solved is if x is equal to 1. So therefore the log of base 2 of 2 is equal to 1. And using this as well, using this law here, we can say that the log of base A of A to the power of B is going to be equal to B, because what's going to happen is the B is going to come down as a coefficient, so it's going to become B of log base A of A, but again, this is equal to 1, so therefore this is just going to become B. With similar logic, the log of base a of 1 is equal to 0. So for example, the natural log of 1 is equal to 0. And again, if you put it in its exponential form, this makes sense because remember this is base e, so it's going to be base e, I'm just call this the power of x for now, is equal to 1. And the only way it's going to be equal to 1 is if it's to the power of 0, because anything to the power of 0 is equal to 1. So therefore, when it's the log of base a of 1, it's equal to 0. And then finally, you cannot log a negative number. It just doesn't work. It's kind of like dividing by 0 or square rooting a negative number. It just doesn't work. And just one other note that's quite important for a lot of these, especially these two up here, these formula up here, is that the actual coefficients need to be the same as well. Like for example, if you had something like 2 of the natural log of 5 minus the natural log of 2, you cannot just pick this part out and then do the natural log of 5 minus the natural log of 2 using this. The coefficients have to be the same, and to do this, what you can do is you can put the 2 as the square here, so it becomes the natural log of 5 squared minus the natural log of 2, and then you can work from there. So here's a few examples of questions that kind of rely around the laws of logarithms. So here we have a question here. So the first thing that we can do is, because we have two logs with the same base adding to each other, therefore what we can do is we can use the law of adding the logs together. So it's going to be log base 3 of 2 times x, which is of course just 2x. And this is equal to 3. And then what we can do, we can write this in the exponential form in order to find x. So the base is 3, so it's going to be 3, and then it's to the power of 3 is equal to 2x. So therefore 2x is equal to 3 to the power of 3, which is 27. So therefore x is equal to 27 over 2. Here's another example. Now remember not to do the mistake of just focusing on these two parts straight away and saying, okay, the natural log of 5 minus the natural log of, sorry, the natural log of x minus the natural log of 5, so therefore we can do the natural log of x over 5, because the coefficient here stops you from doing that. The coefficients need to be the same, so we're going to bring this 2 to the power here first. It's going to become the natural log of x squared minus the natural log of 5 is equal to 2, and then we can do the minus formula. So it's going to become the natural log of x squared over 5 is equal to 2, and then what you can do is put it in its exponential form. Remember this is base e, so it's going to be e to the power of 2, and this is equal to x squared over 5. Times both sides by 5 to get 5e squared is equal to x squared, and then square roots to do x is equal to the square root of 5e squared, which is equal to the square root of 5e. And that's the final answer. Now you could say that it could be plus or minus, and technically this could be true, but when you analyse what x is, you realise that it cannot be minus, because then you would be logging a minus number, which remember you can't do. So there's only one answer, it's plus root 5e. And then here's one final example. So again, remember that you can't just straight away do the plus formula here. What you're going to have to do is put the 2 in first, because the coefficients need to be the same. So it's going to first be log of x minus 1 squared plus log 2 is equal to 1. Add the logs, and it's going to become the log of 2 x minus 1 squared is equal to 1, and then what we can do is put it as exponential form. Remember this is base 10, so it's going to be 10 to the power of 1 is equal to 2 of x minus 1 squared. This is of course just 10, so it's going, well, first of all let's do this first. So it's going to be 2 of, and then this expanded is going to be x squared minus 2x plus 1, and this is equal to 10, because that's 10 to the power of 1. Expand the brackets to do 2x squared minus 4x plus 2 is equal to 10, and then bring the 10 onto the other side to do 2x squared minus 4x minus 8 is equal to 0, and then divide everything by 2 to do x squared minus 2x minus 4 is equal to 0. And then we can solve this. I'm just going to put it into the calculator. You could use the quadratic formula as well, and this will give out the values that x is equal to 1 plus or minus root 5. So x is equal to 1 plus or minus root 5. But if you check with your calculator, if it's minus, then x is going to be a minus number because root 5 is bigger than 1, and therefore you would be logging a negative number. So therefore x cannot be equal to 1 minus root 5, so therefore x is just equal to 1 plus root 5, and that's the final answer. Now, a very powerful thing you can do with logs is to take logs of both sides. So here's an example of a question when we have 5 to the power of x is equal to 2 to the power of x plus 1. So at first this looks very difficult, but something we can do is we can take logs of both sides. You can use any base and log you want. Typically, we just use the log with base 10. So you can log both sides. So you can log this side to do log of 5 to the power of x, and this is equal to, and then we log this side, log to the power of 2 to the power of x plus 1. And we can log both sides because of the very fundamental thing with equations. You can change one side of the equation, as you know, like for example if you wanted to plus 2, if you do the exact same thing to the other side, you plus 2 to the other side. As long as you affect them the same, it's fine. And that's what we've done here. We've affected them the same, we've logged both sides. And now what we can do is we can take these coefficients down like this. So this is going to become x log 5 is equal to, and then this can become the coefficient. Remember to do brackets because this whole thing is going to become the coefficient. So x plus 1 of log 2. We can expand the brackets, so this is x log 5, and this is equal to x log 2 plus, and then 1 log 2 is just log 2. Bring this onto the other side to get all the x's onto one side, so it's going to become x log 5 minus x log 2 is equal to log 2, and then factor out the x to x of log 5 minus log 2 is equal to log 2, and then divide everything by log 5 minus log 2. So this is going to become x is equal to log 2 divided by log 5 minus log 2. And if you put this into your calculator, this is equal to 0.756 to 3 decimal places. So this is a really useful technique, and it's actually something we've kind of done already. If you have 10 to the power of x is equal to 1,000, well, one of the ways we can do this is the way we've done it before, where we do log, and then this is the base, so it's going to be base 10, but again, we don't really write the 10 of 1,000. And this is equal to x, so therefore x is equal to log 1,000, which you put into a calculator is equal to 3. But the other way you can do this is by taking logs of both sides. You can do log of 10x is equal to log 1,000. And then what you can do is bring the x down, so it's going to be x log 10 is equal to log 1,000. And we said in the laws that if this here, at the base, this is 10, is the same as this number, then this is just equal to 1. So therefore this is just going to be x is equal to log 1,000. So therefore x is equal to 3. And from now on, if we get something like this, I'm going to use this method here, because personally I find this a lot easier and it's less likely to make mistakes. Again, it doesn't really matter that much which method you use, because obviously you get the same answer of x is equal to 3, but it's two different ways of doing it. And again, it's the exact same if we're making both sides a base. So for example, if we had the natural log of x is equal to 2, and we wanted to solve this, remember this is base e, so this is going to be e to the power of 2 is equal to x. I'll just leave it at that. E to the power of 2 is equal to x. But the other thing that we could do is make e the base of both the sides. So this is going to become e to the power of the natural log of x, and this is going to become e to the power of 2. Again, we've affected both sides the same, and this still works. And remember, in the laws, the thing with this is that if you do to the power of a number and the base here is the same number, this is just going to be equal to this here. So this is x is equal to e to the power of 2. And again, from now on, I'm going to do it like this, where I say that I make both sides make e the base of both sides. For a question like this, you make e the base of both sides. Again, it doesn't really matter too much because you get the same answer, but it's two different ways of doing it. So here's an example of a question they could ask you. This example is specifically mentioned on the spec, and we've done things like this before, but I'm going to do it with the logging both sides technique. So I'm going to do log base 2 of both sides, so this is going to become log base 2 of 2 to the power of 3x minus 1, and this is equal to log base 2 of 3. I'll go kind of through the full working, but basically one of the powers of this method is you can basically immediately realise that this is equal to 3x minus 1 and write it like that. But just to be full and show what's going on, 3x minus 1 becomes the coefficient, so it's going to become 3x minus 1 of log 2 of 2 is equal to log 2 of 3. This is equal to 1 because the base and this number are the same, so this is equal to 3x minus 1 is equal to log 2 of 3. 3x is equal to log 2 of 3 plus 1, so therefore x is equal to log 2 of 3 plus 1 over 3, which if you put into a calculator is equal to 0.862 to 3 decimal places. So here's another example. Now when you first look at this, this looks quite nasty, but again this becomes so much easier if you take logs of both sides. Now you can use any log you want, but this also becomes a lot easier when you either use a log of base 5 or a log of base e, so a natural log, because then what would happen is this would cancel out and it would just become the power. So you can either basically, to make it easiest, you can either use log base 5 or the natural log. I'm just going to use the natural log. So what I'm going to do is I'm going to natural log both sides. So this is going to be on this side, it's going to be the natural log of 5 to the power of x e to the power of 1 minus 2x, and this is equal to the natural log of 6. I'm going to separate these into two separate logs. So this is going to be the natural log of 5 to the power of x plus the natural log of e to the power of 1 minus 2x, and this is equal to the natural log of 6. Again, remember we can do this because of how plussing logs with the same base works. We can bring the x to the power down, so it's going to become x natural log of 5 plus, and then we can bring this whole coefficient down. Remember to put it in brackets because we're bringing this whole thing down. 1 minus 2x, and this is multiplying the natural log of e, and this is equal to the natural log of 6. And this, because the base is, remember, this is a base e basically, and this is e, this is just going to be equal to 1. So this is x natural log of 5 plus 1 minus 2x is equal to the natural log of 6. I'm going to move the plus 1 onto the other side to do x natural log of 5 minus 2x is equal to the natural log of 6 minus 1. Factor out the x here to get x of the natural log of 5 minus 2 is equal to the natural log of 6 minus 1, and divide both sides by the natural log of 5 minus 2 to get x is equal to the natural log of 6 minus 1 over the natural log of 5 minus 2. Now, I wouldn't be surprised if they ask you to keep it in this form here, but if they want it in decimals, it's equal to minus 2.03. So the final type of question they could ask you is of the quadratic type, and these aren't that bad as long as you understand what is happening, what they've given to you, and especially when you start working these out, use a substitution. This really helped me at the start. So here's an example of this where we have 2 to the power of 2x minus 4 and then 2 to the power of x minus 12 is equal to 0. And the key to this is realise that 2 to the power of 2x is equal to 2 to the power of x squared, and therefore what we can do with this is now the quadratic kind of element with it, because what we can now do is make a substitution in order to turn this into a more easier to view quadratic by saying that u is equal to 2 to the power of x, and we can rewrite this now as, remember that this is 2x squared, that this is going to be u squared minus 4, and then 2x is u, minus 12 is equal to 0, and this is a much easier quadratic to deal with, which you can easily solve, which you've learned before. I'm just going to do it by factorising with the u here, and the u here is equal to 0, then this is minus 6, and this is plus 2. So therefore, u is equal to 6 and minus 2, and therefore, as u is equal to 2x, therefore we just sub this back in. 2 to the power of x is equal to 6 and minus 2, and then we can solve it from here. So 2 to the power of x firstly cannot be equal to minus 2 because a power cannot be a negative number, but 2 to the power of x can be equal to 6, and what we can do is we can just log both sides by base 2, so it's going to be log base 2 of this side, so it's going to be 2 to the power of x is equal to log base 2 of 6. I'm still kind of doing this the quite long-winded way, but it's kind of a lot easier to do it in your head and very quickly when you've done it enough. Bring the x down to x log of 2 of 2 is equal to log 2 of 6, and therefore this is equal to 1. So therefore x is equal to log base 2 of 6, which is equal to 2.58, 2 decimal places. So x is equal to 2.58. So here's another example. Now when you first look at this might not be immediately obvious how this is a quadratic or how we solve it. And the key to this is writing this out as a fraction. So this is 2e to the power of x minus 14 over e to the x, and this is equal to 12. And what we can now do is, this is really awkward to be in the denominator. It's kind of awkward for any kind of algebra to be in the denominator. So what we can just do is times everything by e to the power of x. We know that e to the power of x is not going to be equal to 0. You know, when you times everything by a number, if it's equal to 0, then it just goes wrong. We know that a power can't be equal to 0. So therefore what we can do is times everything by e to the power of x, and this will become 2 of e, and it will basically be to the power of x times e to the power of x, which is going to become e to the power of 2x, minus 14 over e to the power of x, which is going to be minus 14, and this is going to become 12 e to the x. And now we have this traditional quadratic. We can bring this onto the other side to do 2e, 2x minus 12e to the power of x minus 14 is equal to 0, and then we can make the substitution by saying that u is equal to e to the power of x, because remember this is the same thing. E to the power of 2x is equal to e to the power of x squared, and this is where the quadratic comes from. So u is equal to e to the x, so therefore 2, and this is going to be u squared as we just said, and it's going to be minus 12ex, it's going to be minus 12u minus 14, and this is equal to 0. We can divide everything by 2 to do u squared minus 6u minus 7 is equal to 0, and then we can factorize, so this is going to become u like this, and this is going to be equal to minus 7 and plus 1, so therefore u is equal to 7 and minus 1, and as u is equal to e to the power of x, e to the power of x is equal to 7 and minus 1. E to the power of x cannot be equal to minus 1 because a power can't be equal to a negative number. So therefore, e to the power of x is equal to 7, and therefore we can natural log both sides, do the natural log. Again, I'll do it the long way. E to the power of x is equal to the natural log of 7, and therefore it's x natural log of e is equal to the natural log of 7. So therefore this is going, because this is 1, this is equal to x is equal to the natural log of 7. I'm kind of hoping when you do, this is what happened to me, when you do enough examples, you can kind of actually skip these two steps kind of immediately, realize that if you natural log this is just going to become equal to x, and therefore it's just going to become the natural log of 7. That's why I prefer this method, because it becomes quicker and a lot more accurate over time. It's kind of a way to think about it. So finally, they could ask you to do a quadratic of a logarithm itself. This is the exact same thing, it's not too bad. The only thing I just want to remind you, and this is kind of the only time this actually ever comes up, is that this log x squared, please don't say that this is equal to 2 log x. That is only the case when it is log of x squared directly. It's the x squared, not the whole thing squared. Please remember that, and therefore because of that this is an actual quadratic, and we can use the substitution u is equal to log x, and therefore we can do 2, and this is log x squared, so this is going to become 2u squared is equal to 20 minus 3u, because there's the log x here. Move this onto the other side to do 2u squared plus 3u minus 20 is equal to 0, and then we can solve this quadratic. I'm just going to use a calculator to do it, and say that u is equal to 5 over 2 and minus 4. So as u is equal to 5 over 2 and minus 4, therefore log x is equal to 5 over 2 and minus 4, and then we can just solve it from here. So log x is equal to minus 4, and therefore we do the thing where we do the 10 as the base of both sides is equal to 10 to the power of minus 4, and therefore remember that this is just going to be equal to x. So x is equal to 10 to the power of minus 4, which is equal to 1 over 10,000, and then log x is equal to 5 over 2, so therefore 10 to the power of log x is equal to 10 to the power of 5 over 2, so therefore x is equal to 10 to the power of 5 over 2, which is equal to one decimal place 316.2. So x is equal to 1 over 10,000 and 316.2. So here's a couple of questions on laws of logarithms. So pause the video, have a go, and I'll go through the answers in about 5 seconds. So for question 1 part I, it wants us to express b in terms of a. So we need to make b the subject basically, and then a will kind of be the terms on the other side of the equation. So the first thing we should probably do is combine these two logs, so therefore we can make 3 the base on both sides from there. So this would be equal to log base 3 of 3b plus 1 over a minus 2, and this is equal to minus 1, and then make 3 the base on both sides, so this is going to be 3 to the power of log base 3 of 3b plus 1 over a minus 2, and this is equal to 3 to the power of minus 1. We've just made 3 the base on both sides. When it is this number and this is the same base, then this means that it's just going to be this. This side is going to be 3b plus 1 over a minus 2. We talked about that in the laws, and this is equal to 3 to the power of minus 1, which is equal to 1 over 3. And now we just need to make b the subject. So first of all, let's times both sides by a minus 2 to get rid of this denominator. So this is going to be equal to 3b plus 1 is equal to 1 over 3 a minus 2. So this is 3b plus 1 is equal to 1 over 3a minus 2 over 3. Move the minus 1 onto the other side to do 3b is equal to 1 over 3a minus 5 over 3, and then divide everything by 3 to get b is equal to 1 over 9a minus 5 over 9, and that's the final answer. So for the second part, I don't really know why these are kind of labelled part A and part B, because they don't really have anything to do with each other. This is just a completely separate question. So this kind of looks like the quadratics that we talked about before, because you have the 2x and we have the x here. But we have this plus 5, which kind of complicates things a tiny bit, because what can we do with this? Well, remember that 2 to the power of 2x plus 5 is equal, if you remember the indices laws, 2 to the power of 2x times 2 to the power of 5, because remember when you times powers they add together, so it's 2 to the power of 2x times 2 to the power of 5, which is equal to 2 to the power of 2x times, and 2 to the power of 5 is 32, and this is therefore equal to 32, just written in a different way, times 2 to the power of 2x. So we can write this as 32 2 to the power of 2x minus 7 2x is equal to 0, and this is the quadratic that we're really familiar with, because this is the kind of x squared part and this is the x. If we make the substitution, u is equal to 2 to the power of x, this will become 32u squared, because remember 2 to the power of 2x is 2 to the power of x squared, minus 7u is equal to 0, and therefore we can solve from here. The first thing we can do is factor out the u to do u of 32u minus 7 is equal to 0, and therefore we can equalize the 0 individually, where this is u is equal to 0, and then this is going to be 7 over 32. So u is equal to 2x, so therefore 2 to the power of x is equal to 0 and 7 over 32. So 2 to the power of x is equal to 0, but 2 to the power of x cannot be equal to 0, because you cannot have a power that's equal to 0. So therefore the only thing is 2 to the power of x is equal to 7 over 32. And I'm going to do log base 2 of both sides. Do log base 2 of 2x is equal to log base 2 of 7 over 32, and I'm just going to write this. This is kind of why this is a beneficial method, because then you can just realise quickly this is equal to x, and this is log base 2 of 7 over 32. And it wants it to 2 decimal places. And if you put this into a calculator, this is equal to minus 2.19. So that's the final answer. So for question 2 part 1, the first thing that we really need to do is to put this 2 into this bracket here, and I'll kind of show why in a sec. So this needs to become log of x plus a squared is equal to log of 16a to the power of 6. And the reason we want to do this is because then we can make 10 the base on both sides, like this, is equal to 10 to the power of log of 16a to the power of 6. And again, the law is, remember that these have the base of 10, and because this is the same here, this is just going to be equal to x plus a squared, and this is going to be equal to 16a to the power of 6, as this has the same base as well. Now remember that law. But the one thing that's important is this 2 needs to be in this log here in order to do it. So if the 2's here, it doesn't work. You need to put this 2 into this log here first. Now I must admit, this next bit I didn't actually get straight away. I kind of had to look at the mark scheme a bit because I didn't immediately see this. The first thing I tried to do was expand this bracket, although I did kind of realise straight away that it would be a bit of a weird idea, because this is a really high power, and when you're introducing like x squared and a to the power of 2, stuff like that, it's just going to get more and more complicated. So the thing you actually do here is square root both sides. This is going to be x plus a, and this is going to be the square root of 16a to the power of 6, which is going to be equal to 4a to the power of 3. I immediately didn't get that. The more I look at it, the more it does make sense, because this is such a high power that you probably are going to have to reduce it in some way, and the way you do that is by square rooting. And then obviously this is really nice as well, because this easily square roots to this. So just keep an eye out for that. This is quite a hard question, I must admit. I didn't see that straight away in terms of that kind of tactic. And then you can move the a onto the other side to do x is equal to 4a to the power of 3 minus a. And that's the final answer. There isn't actually too much working. It's just kind of this kind of step here that's the hard bit that really gives you the 3 marks. So just watch out for that. Again, it is a bit of a tough question, so maybe don't, it's not the end of the world if you didn't get that, because I think that's an abnormally hard question. So for the second part of 2, the first thing that we should probably do is simplify this by doing the division of the log. So it's going to be log of base 3 of 9y plus b over 2y minus b, and this is equal to 2. And then we're going to make 3 the base of both sides. So this is going to be 3 log of base 3 of 9y plus b over 2y minus b, and this is equal to 3 to the power of 2. We've made 3 the base of both sides. This is just equal to 9y plus b over 2y minus b, and this is equal to 3 squared, which is 9. And then what we're going to do is we're going to times both sides by 2y minus b to get 9y plus b is equal to 18y minus 9b, and then we need to make it in terms of, so we need to make y the subject, sorry. So I'm going to move the 18y onto this side to do minus 9y plus b is equal to minus 9b, and then put the b onto this side to do minus 9y is equal to minus 10b, and then I'm going to divide both sides by minus 9 to get y is equal to 10 over 9b. And that's the final answer. Y is equal to 10 over 9b.